Alright, this is the final section of Chapter 5, 5.7. This deals with logistic functions and Gompertz functions. So a logistic function, A, B, C, are real numbers, okay? This is what a logistic function looks like. A is down here, it's the number in front of E, that's the number E, like the natural base. And then B is the number in front of the only variable in this thing, and that's the exponent there. And then C is your numerator. If A is positive, a logistic function will increase when B is greater than 0 and decrease when B is less than 0. Okay, so assuming A is positive, we get growth if this B right here is positive. We get decreasing when B is negative. Now, instead of B being negative, your exponent will actually end up being positive. Okay, when B is positive, this exponent will actually end up being negative. I know that seems weird. Why would they not just write it the other way around? Well, they want it to increase when something's positive and decrease when something's negative. So if we didn't have that negative there, it would be backwards, and it would be increasing when something's negative and decreasing when something's positive. So just to kind of make it do what seems natural, increase when it's positive, decrease when it's negative, we stick that negative in there in front of the B. Okay, C in this thing is called the ceiling. It's like the maximum value that the function can take on as x goes to positive or negative infinity, depending on the value again of B, if it's increasing or decreasing. But that's what I call C, is the ceiling. Okay. Excuse me. Alright, logistic growth. Again, same exact formula. If you look, there's no difference in this. C, 1 plus, 1 plus. A, e to the negative bx, a to the negative bx. It's just, logistic growth just means what we said. A is positive and B is positive. Now, if you were to graph this, if you plug in a number for C, a number for A, a number for B, and all these criteria are met, if you graph this, you don't have an x-intercept, okay? This thing has a horizontal asymptote at the x-axis. Your y-intercept would be C divided by 1 plus A, right? Literally whatever these numbers are. It's like this part goes away, right? And then your horizontal asymptote is y equals 0, again the x-axis, and then y equals c, again whatever our ceiling is. That's what we're saying. It gets closer and closer and closer to there as we go off towards infinity, but it can never attain that value of c, no matter how big we get. It'll get close, but it'll never get there. Alright, then logistic decay, same exact thing, except now b is negative. So we attain that value of c as we go off in the negative direction, and we come down towards 0 as x gets bigger and bigger and bigger and bigger. Alright, now the idea behind logistic growth and decay is we have that look of an exponential at the beginning. Something bends upward and it starts to grow extremely fast, or in this case starts to decay extremely fast. But the idea here is, you know, the amount of no matter what, the amount of energy or the amount of space or whatever needed for something to grow in this extreme fashion eventually runs out, and we don't have enough room to keep growing at that rate, or we run out of resources to grow at that rate, and things start to cool off. Right? In sales, you know, if a company starts taking off and growing like this, well, what happens? All the competitors find out what this person's doing, then they come in and flood the market, and then things level off with their sales, right? So that's the idea of logistic growth. It's basically things can't grow exponentially forever, so they have to level off, and that's why we have this logistic growth model. It's more realistic for long run than exponentials. Alright, so here's an example selling of iPods. So I don't know about you, but I was one of the late people to get an iPod, but I know a lot of my friends got them when they first started coming out. And anyway, the number of iPods sold just exploded right at the beginning, but then as the market started to have competition, other companies made MP3 players, and eventually iPads is what we're referring to here. iPads and Android tablets and players came into being, smartphones. Then the sales of iPods started to slow down, even come down a little bit. Alright, so what we want to do in this problem is take this data set, make a scatter plot, and find a logistic model for the data. So just like we've been doing, we're going to throw this data into our calculator using the stat menu, and then we're going to run regression, but we're going to use logistic regression. Alright, I've got the data all in here now. Notice a couple of things. One, that the list 1, the x's are to be x is equal to the number of years after 2000, so 2002 is 2 years after, 2003 is 3 years after, and on and on. And then y is equal to the number of millions of iPods, so 376,000 is 0.376 million. 937,000 is 0.937 million. Now if you aren't good with decimals or percentages, just take the number that you're given, like 937,000, and if you want to know how many millions that is, divide it by a million. Alright, so 0.937. So that's what I'm doing here, but you know, you can do them in your head. And then from there on, it's just, there's where the decimal goes, 4.416, 22.497. This is how many millions there are. Alright, so there's where that list is coming from. It's in millions. Alright, so x is in years after 2002, y is in millions. Alright, part A wants us to create a scatter plot of the data. So, second, turn your stat plot on, hit 1 here. Alright, turn that on, and then that's scatter plot. So remember, once you've got the plot 1 on, press zoom 9, it'll make a scatter plot of your data. So there's our scatter plot of our data. So it has that look. It starts off kind of flat, and then it explodes for a while, and then it kind of levels off. Right, this one actually even comes back down a little bit. Alright, now we want to create a scatter plot. If I wanted to do it on a graph, just press the trace button. There's 2.376, and just plot those points on your graph. And just press left and right, plot the points if you wanted to actually do that. Alright, but I'm going to cheat and say, alright, there's my answer for part A. Alright, part B, find a logistic function model to model the data and graph the function with the scatter plot. So for part B, we're going to run that logistic regression I was telling you about. So second mode, to go back to your home screen, press stat, come over here to calc. Alright, and then you're looking for logistic regression. Alright, so there it is. Not LN regression, not LIN regression. Alright, logistic regression. So hit logistic. I'm going to press vars. Come right over here to y vars function y1 and tell it to store it in my calculator in the graphing menu. So it runs its thing. It takes a little while to do logistic regression, just because it's a more complicated regression than linear, quadratic, or any of that. Alright, and there is our model. C is 53.3 excuse me, 349 to 3 decimal places. Right, there's our A, and then there's our B. So I'm going to say y equals alright, C, let me extend this page real quick. Alright, and there is our model. I went ahead and threw it in here. 53.35, that's our C, and it goes up top, divided by parentheses, so all this is the denominator. 1 plus A was 6365.00, So the 2 decimal places, that's just 6365. E to the power of negative 1.66. Alright, again to 2 decimal places, and then just x. Alright, so there's our model. Sorry. And it also wants us to graph it along with the scatter plot. So I've got it stored in y1, again because I put y1 at the end there. So if I hit graph, it'll actually put that regression function in there. Alright, again, now notice that a logistic model, logistic growth, will flatten out and then it'll just stay almost horizontal, almost parallel to the x-axis the further and further and further you go. So our data kind of suggested a dip in sales at the end. Right? Logistic model was just going to level off at the end. Okay, so it's not going to show that little dip, but it does show the leveling off that took place there towards the latter part of the decade. Alright, so I'm going to put that in there and cheat and call that my graph. Alright, so there's part B. Now, part C says, use the model to estimate the number of iPads sold in 2015. Alright, now remember, 2010 was our last data point. So that's like this right hand side here. I'm going to use the model. Now I can do it one of two ways. I can hit second quit, and I can go back into the vars menu. Since I have it stored, since I took the time to do that, I can just come over here to yvars, hit enter for function, hit enter for y1, and I can say, alright, evaluate it at 2015, which means x is 15, and hit enter. Alright, and I get 53 point roughly 35 million. So let me plug that in here real quick. 53.349. Or using the notation we had up here, that would be 53,349,000. 9,000 iPods. Now the other way that I could have done that is go to your graph screen, and remember your window, the X max is the biggest X you can put in there, so make it go beyond 2015, like 16. Alright, 16 would mean 2016, and regraph everything. Okay, so there's my function again. Notice it just levels off, it's almost parallel to the x-axis. Now hit trace on your calculator, press down, make sure you're not in your points, press down if you're in the model, and now press 15. And there's again another way to approximate it. So either way would work. I'm going to go zoom 9, zoom back to my original, just in case I need to come back to it. Alright, part D says, what is the upper limit for the number of iPods sold according to the model? Remember, the upper limit is C, whatever C is. So the upper limit, according to the model, is 53.35. Now, what does it say? Does that seem reasonable? Yes. I mean, this is the most iPods it could sell ever, you know, as far as X going beyond 2000. And because of that trend coming downwards, because of smartphones, because of Google getting into the marketplace, and just other companies, not just Google, but other companies getting into the marketplace, it's definitely reasonable to see it never get beyond that number. Okay, we didn't even we went beyond it a couple of years, but because of that dip down, and because of the competition factor, it doesn't seem reasonable to go back, you know, drastically beyond that unless they come up with some crazy new feature that the iPod has that the others just don't have. Alright, another data set. This one giving us average miles per gallon of gasoline for passenger cars from 1975 to 2006. We want to find the logistic function that models these data. Alright, so again, just practicing going through the calculator and doing this. So put all this in. X is now years after 1970, so make sure you're starting with 5 and then 10 and not, putting the years in there. My calculator still has the data from the last problem. Just a reminder, we've done this in other videos before, but just a reminder, go to the top of the list name, hit clear and enter, and that'll clear out the entire list, so you don't have to go through and do it one by one. So top of the list, clear, enter. Alright, and then just start putting in your data. So 5, 10, 15. Alright, I got my data in there now. So list 1 again is the year after 1970. Alright, list 2 is the average miles per gallon for passenger cars that year. Okay, so we're going to do logistic regression just like we did before. So after we got our data in, stat, come over to calc, look for logistic. Alright, hit enter. Again, it takes a little while. If you need to store it in your calculator, vars, yvars, function, y1. Alright, enter. And again, it takes a while, so I'm going to pause it. Alright, so there's what my calculator returned. I went ahead and threw down everything here. I went ahead and did the 4 decimal places this time. So there's C. Right, there's the A, and then there's the B. Okay, and don't forget to put your little negative sign out there. Again, the model is told to you what everything is up top. So C is over top of everything. There's the A, there's the B. Just plug it in there, and remember to do it correctly. Alright, remember, if you need to ever make a scatter plot of it, second, make sure your stat plot 1 is on. Hit enter. Zoom 9. So there's our data this time. Okay, so again, a logistic model does a good job here, and big strides were made in miles per gallon of fuel efficiency there at the beginning. But then once it became like a must, once everybody started making their cars more fuel efficient and became a competition, it's just harder to maintain that level of increase. You just can't maintain it forever, so it started to level off. Now, if you're starting to look at like hybrids and everything like that, then yeah, it's going to dip back up again, because we're going to start talking about 40 and 50 miles per gallon. So it would dip back up again. But this is just passenger cars. It's not talking about hybrids or anything like that, fuel cell cars or any electric cars of the future or anything like that. So that's what a logistic growth model should look like. So if you see a scatter plot like that, a logistic growth model should do a pretty good job. Alright, and then the Gompertz functions, they are extremely weird in the fact that they have an exponent within the exponent. Okay, if you look at the logistic models we've been dealing with here, yeah, there's an exponent, and there's an exponent, and there's multiplication in the exponent. But the Gompertz functions, we have an exponent, and then that exponent has an exponent. Okay, so they're a little bit different than the logistic models, but they both have the same kind of characteristics that we have this initial period of growth, alright, and then a rapid growth, and then a leveling off. That's what both of these functions have going on with them. Alright, so just kind of a rundown of what everything is. R is some number, some proper fraction, a number between 0 and 1, alright, that we're multiplying or raising to this t power. Alright, and then C is your maximum possible number of individuals. Okay, so that's going to come up in our example here in just a little bit that we're going to be doing. Alright, A represents the proportion of C present when t equals 0. Alright, so let's go through this question. So this equation right here, this is a Gompertz equation because we have 0.06 being raised to the 0.2 and then 0.2 being raised to the t power. So this predicts the size of a deer herd on a small island t decades from now. So what is the number of deer on the island now when t equals 0? Alright, so for part A, we're just plugging in 0 for t. So we've got 1,000. We're multiplying that by 0.06 raised to the 0.2, and that 0.2 raised to the 0 power. So that's where the 0 is coming from. Now remember, what's anything raised to the 0 power? This right here is equal to 1 because anything raised to the 0 power is equal to 1. So we get 1,000 times 0.06 raised to the 1, which is just 1,000 times 0.06. Alright, then what's 1,000 times 0.06? 3 zeros, so move that decimal to the right 3 times. So 1, 2, 3 will give me 60. Alright, or 6% of 1,000, whichever way you want to think of it. Alright, so that's part A. There are 60 deer. Alright, part B says, how many deer are predicted to be on the island 1 decade from now, when t equals 1? Okay, well, now just do the exact same thing we did in part A, 0.06, and now raise that to the first power. That's 1,000 times 0.06 to the 0.2 power. Alright, now go to your calculator for a problem like this, and be careful as you're putting these in. That's 1,000 times 0.06, and then that's raised to the 0.2 power. So 569.68. Alright, we're going to round it to the nearest whole number because this is a deer, so we're going to say about 570. Alright, now part C, graph the function. So I went ahead and cheated and went ahead and got a graph of this from the book that I got this problem from. So this is basically what the graph will look like: 1 decade, 2 decades, 3 decades. So notice in that first decade and about halfway through to the second decade, extremely rapid growth in the population of the deer, from starting at 60 to almost, up to 1,000. Alright, but then it levels off, just like the logistic growth. It eventually levels off. Alright, part D says, what's the maximum number of deer predicted by this model? C, which is out in front of the A to the R to the T, C is the maximum possible number of individuals. So here, that's 1,000. So according to the model itself, 1,000 deer is the maximum. Alright, and then the last part. Let me extend this one more time. It's going to take a little bit of room. For part E, it wants us to, how many years will there be 840 deer on the island? So that means we want to take, remember, this gives the number of deer, predicts the size of a deer herd. N is the number of deer, so that's what's going to be 840. So 840 equals 1,000 to to the 0.06 to the 0.2t. Alright, and what are we doing? We're solving this thing for t. Yeah. So, first thing we're going to need to do, we're going to isolate the exponential part. Remember, this is like an exponential function now. So we're going to isolate the exponential part, so we need to divide away the 1,000. Alright, so 840 divided by 1,000 is 0.84. And what are we left with? 0.06 to the 0.2t. Alright, now what are we going to do from here? Or, sorry, 0.2. Let me fix this. Sorry, I made a little error here. That's 0.2 to the t power. 0.2 to the t instead of times t. I already had forgotten that we're dealing with, we're not dealing with an exponential function. Okay, we're dealing with a Gompertz function. So we're going to bring in logs to solve this. So the first thing we're going to do, I'm going to bring in a log on this side. 0.84 equals the log of 0.06 to the 0.2 to the t. Alright, now what is that going to allow me to do? That's going to allow me to take this whole entire power and bring it down out in front here. So I'm going to have log of 0.84 equal to 0.2 to the t times the log of 0.06. Alright, now remember, we're still trying to isolate this t, and it's still in the exponent. So let's divide away the log of 0.06 from both sides. Going over here. Alright, and what do I have left? I have the log of 0.84 divided by the log of 0.06 is equal to 0.2 to the t, right, because this part's gone. Now what do I need to do? I'll come up here. I need to bring in a log again because it's still in a log inside a the exponent is the variable, so I need another logarithm. So I'm going to bring in the logs again, the log of the log. So the log of 0.84 divided by the log of 0.06 is now inside the log. Right, and that equals the log of 0.2 to the t power. Oops. Did it again. 0.2 to the t power. Now again, just like before, this is going to allow me to bring that t down. So I get the log of 0.84 divided by the log of 0.06 is equal to t times the log of 0.2. Right, because that t gets to come down in front. Now last thing, divide both sides by the log of 0.2. And you've got t exactly. Right, your exact answer, t is equal to exactly the log of 0.84 divided by the log of 0.06. All of that divided by the log of 0.2. Alright, I'm going to throw that in my calculator and get a good approximation. Alright, moving this over here so we can see it. Log of the log of the log. Alright, log of parentheses, this is the numerator log, divided by this is the denominator log. Alright, close that. That's all inside of this log, and then that's divided by this log in the denominator. So we get t equals approximately 1.728. And that's decades. So that's 1 year and 0.728, right, parts of a year. So if you want to multiply that by, say, like 12, that's how many months it is, right? Or if you wanted to take 0.727975 and multiply it by 365, that's how many days. Alright, so 1 year, 265 roughly days. Before what? Before the population of deer gets to 840. Alright, now that's a, that's a lot of ugly, math. It's not really complicated. It's just log properties. You just got to understand your log properties. But there is a way you can do this on your calculator. So again, assuming that you throw this model in your calculator. Alright, so I've got this in my calculator, 1000, 0.06 raised to the parentheses, all of this is the exponent, 0.2 to the x. Okay, again, I'm using x instead of t. If you've got your plot 1 on from the last problem, make sure to go up there and turn it off. Alright, I'm going to hit enter to turn that off. Now briefly I'm going to hit zoom 6 to bring it back to the original window. Alright, but again we're getting values up close to 1,800, so we're going to extend our window. Alright, so I changed my window to this, -1, just to have something to the left side of the y-axis, just so we can see the y-axis. And then there's the x max of 10, because again our answer ended up being just 1.728 down there, so we didn't need anything extremely large. So I put positive 10 there. You could even put something like 5. But then down here for our y min and y max, I've made the y max 1,000 and the y scale 100, just because that's, again, 1,000 was our maximum value from the original formula. Alright, so graph that. So there's our function, and notice once it gets to close to 1,000 it just levels off. Alright, what are we looking for? We're looking for where it gets to 840 deer. So type in the second one, y2 840, graph that, and there's our intersection that we're trying to find. So option 5, intersect first curve, that's our function right here. Second curve, that's the horizontal line at 840. Alright, and then for our guess, let's try to get close. Alright, and then there's again the 1.72. So you can do it with your calculator. Just remember, left side one of the y1s, or one of the y's, right side and the other, and then find that intersection. That'll always work for any of these equations.